Welcome you all to the lecture series of Digital Electronics QE 039/049. Myself Dr. Kishanu Kundu, Assistant Professor, Department of Electronics and Communication Engineering, GL Bajaj Institute of Technology and Management. So, we are in lecture number 31 and here we are discussing about digital logic families. Already we have discussed 3 parts of digital logic family in the previous 3 lectures. There we have discussed the introduction of digital logic family, we have discussed few examples like DTL, RTL, DCTL, TTL, ECL logic family, and in part 4 we are going to discuss the last example, that is called CMOS logic family. So, let us start. CMOS logic family is the CMOS logic family is a group of logic circuit built with complementary MOS device. What is MOS? Metal oxide semiconductor. MOS, yeah, MOSFET, metal oxide semiconductor. Okay. All logic gates that are built as MOSFET device will come under the MOS logic family, MOS. MOS logic family can be classified into 3 categories, very important. There are 3 categories of MOS logic. What are they? NMOS logic family built with N channel metal oxide semiconductor FET. What is FET? FET is field effect transistor. Field effect transistor is very important topic of analog circuits. Okay. So, NMOS stands for N channel metal oxide semiconductor field effect transistor. Next is PMOS logic family. PMOS, what is PMOS? P channel metal oxide semiconductor field effect transistor. And if you do not have the knowledge of P and N, so PN diode we are having, this is PN junction diode. P is more number of holes, okay, and in N more number of electrons. This is a basic concept. CMOS, complementary, that is combination of both N channel and P channel, that is called complementary. CMOS, complementary MOS, complementary MOS. Among the MOS families, NMOS and CMOS are used in making an integrated circuit. It is because of their advantages. So, mostly when we go for some integrated circuits, we prefer NMOS and CMOS. Okay. Let us proceed. So, we will start with NMOS logic circuit. This is N channel metal oxide semiconductor field effect transistor. So, in N channel MOS family, current conduction is because of the electrons. Already we have told that N channel is more number of electrons. Okay. So, here current conduction is due to electrons. In P channel the current conduction is due to holes. Okay. So, in N channel current conduction is because of electrons. The negatively charged electrons are fast moving than holes, which is positively charged. So, electrons are negatively charged and holes are positively charged. So, the speed of operation of NMOS is faster than PMOS. That is why we are using NMOS in most of the integrated circuit. It is a very important question, that why you are preferring NMOS? Because of its speed, right. NMOS is preferred over PMOS because of its speed. Next, now we will discuss a NMOS inverter circuit. Already we know what is inverter. NOR gate, NOT gate. NOT gate means if we are giving 0, output is 1, if we are giving 1, output is 0. This is the NOT gate. So, now this we are going to implement using NMOS. So, here you can see that two FETs are used, field effect transistor, one Q1 and one Q2. Okay. The NMOS inverter circuit has two n channel MOSFET device. There are two n channel MOSFET device Q1 and Q2. It is visible, the lower portion, right. The NMOS inverter circuit has two n device. Among the two MOSFET, Q1 act as load MOSFET and Q2 acts as switching MOSFET. So, Q1 is nothing but the load MOSFET and Q2 act as a switching MOSFET. Okay. Since the gate is always connected to supply VDD, here you can see that gate is connected to supply VDD, the MOSFET Q1 is always on. Okay. So, that internal resistance of Q1 act as the load resistance RL. Compared to both MOSFET, Q1 is designed to have more resistance than Q2. So, when 0 voltage is given at the gate terminal of Q2, it is turned off. So, when we are giving logic 0 to Q2, it is making Q2 as off, turn off. It will make the output V0 be high. If Q2 is off, then V0 is connected directly to Q1. So, Q1 will be high, this is off, right, Q1 will be on. When high input is given to gate terminal of MOSFET Q2, when we are giving logic 1 to Q2, in that case when we are giving high input to logic 1, then Q2 will be on and this will be acting as a closed switch. So, V0 will be connected to ground, means the output will be 0, the output will be 0. So, very simple. Once more I am telling, when we are giving 0 logic low voltage to the input of Q2, then that will, in that case Q2 will be turned off and then the V0 will be connected directly to the this VDD. So, it will be high output, but when we are giving high input to Q2, Q2 will be on, it will act as a closed switch and that case V0 will be connected to the ground and it will be having low voltage. So, it is we are giving low, we are giving high and we are giving logic 1, we are giving logic 0. So, it is just as a inverter, NOT gate. So, the same thing we have implemented using NMOS circuit. Okay. Next, now we are going to implement NMOS NAND gate, right. You know the NAND gate, when both are 0, the output will be 1, when any one of the output is 0, the output will be 1, but when both are input are high, the output will be 0. So, this is the truth table of NAND gate, this is the truth table of NAND gate. Then now, this truth table we are going to implement using NMOS. Okay. So, here you can say see that 3 n channel MOSFETs we have used. Previously we are using 2, here for inverter we are getting 2 n channel MOSFET, here we are using 3 n channel MOSFET, in which Q1 act as a load resistance, Q2 and Q3 act as a switching MOSFET. So, here Q1, previously Q1 also load MOSFET, here also Q1 is load MOSFET, but Q2 and Q3 acting as a switching MOSFET, Q2 and Q3 is acting as switching MOSFET and we are getting output from this point. Okay. So, let us check The two inputs A and B are given to MOSFET Q2 and Q3 respectively. We are giving these two inputs A and B. So, now these are the conditions A and B. So, when A and B both are 0. So, both 0 means Q2 will be also off and Q3 is also off. If both are off, then output is connected directly to VDD, means output is high, very easy. Okay. Next what will happen? Now, when A is 0 and B is 1, means Q2 is off at Q3 on, but if Q2 is off, means this is open circuit. Q2 off means it is open circuit. So, V naught is directly connected to VDD, means V naught is 1 high. Okay. Next case, when A is 1 or B is 0. So, this will be working, but this is off and this is off, means here it is, from this it is open circuit, from this it is open circuit. So, if it is open circuit means V naught will be connected to this VDD. So, high output. And the last case, when both are on 1, when both are 1 means both are working, means this is short circuit. So, V naught now will be connected to the ground, V naught will be connected to the ground, means this is the low output. Okay. Same thing has been written here, we can discuss. When both inputs A and B are given low, both MOSFETs are turned off, which makes the output V naught as high, obviously V naught will be connected to the VDD. Next, when either A or B is low, the MOSFET with low input will be turned off, thus making the output to be high again. And now, if both are high, if high input is given to both the input terminals, it will turn the MOSFET Q2 and Q3 on, these are on. You can see the down line, right. When both are input is 1, the Q2 and Q3 are on. So, in that case, therefore, the current due to the supply voltage VGD will flow forwards the ground, making the output as low, because V naught is directly connected to the ground in that case. So, the output will be low. So, this is the truth table, and same as, see, this is 0 0 1, 0 1 1, 1 0 1 and 1 1 0. So, we have implemented NAND gate using NMOS logic. Okay. Good. Now, this is NMOS NOR gate. What is NMOS NOR gate? NMOS NOR gate means when both are 0, output will be 1, but if any one input is high, the output is 0. So, this is the NOR gate NOR gate truth table. So, this thing we are going to implement using NMOS circuit. Okay. So, you can see here Q1, Q2 and Q3, right. So, 2 input NMOS NOR gate, it has 3 n channel MOSFET, in which Q1 acts as a load, this is acting as a load resistance, and these are the Q2 and Q3 as the switching devices. Okay. But previously it was joined in series, here it is connected in parallel. If low input is given to both the inputs, it will turn off both the MOSFETs, right. If both the 0, it will both are cut, so connected will be output, so it will be 1 high, obviously. Next, what will happen? If A 0 and B 1, A 0 and B 1, so A 0 means this is off, this is on, B on. So, V naught will be connected to ground, because that is working as a closed switch. So, V naught will be 0, V naught is 0. Next case, when A is 1 and B is 0, A is 1 means this is working, this is not working. So, this is act as a closed switch. So, V naught will be directly connected to the ground, means V naught will be 0. Okay. And the last one, when both are 1, then both will be working. So, in this any path V naught can choose any path and it is directly connected to the ground. So, it will be 0. Okay. So, you can see that if low input is given to both the inputs, it will turn off both the MOSFETs Q2 and Q3, hereby making the output to be high. If any of the input either A or B is given to high input, the corresponding MOSFET is high input will turn on, making the output to be low. Similarly, if the both inputs are high, it will turn on both the MOSFET, which will make the output as low. Okay. So, you can see that this truth table is resembling to this truth table of NOR gate. So, here we have implemented NOR gate using NMOS. Okay. Good. Next is PMOS logic. The PMOS operation is similar to NMOS circuit, except that the mode of conduction is different. Okay. For P channel MOSFET, a negative voltage is given to the gate terminal to create a channel. Thus, negative voltage is enough to turn on the PMOS devices. This is the main important difference between PMOS and NMOS. Here the negative voltage, low voltage is enough to turn on the PMOS devices. Okay. Next. Now, we will discuss in detail about the CMOS logic family. Whatever we have discussed so far is NMOS and PMOS. Now, we are moving into CMOS logic family, and that is called complementary metal oxide semiconductor field effect transistor logic family. It is using both N channel and P channel MOSFET devices. Already we have told CMOS is using both P channel and N channel MOS. CMOS has greater complexity than PMOS and NMOS. However, the speed of operation is high and power dissipation is less. This is a very important point of CMOS, that here the speed is very high and power dissipation is low. Okay. And in addition to that, has more fan out and better noise margin. Already these characteristics of logic families, fan out, noise margin, already has been discussed in previous slides, previous lectures, you can refer that. Okay. So, now let us make some circuit using CMOS logic. So, we are going for the CMOS inverter. Okay. What is inverter? NOT gate. Again we am telling NOT gate means if you are giving 0, it is giving 1 output, is giving 1 as input, it is giving 0. Okay. So, CMOS inverter. So, here you can see that Q1 and Q2. Okay. So, both the N channel P channel devices are connected. It is P channel and N channel. The negative I have told na, this is one, this point, one bubble is there. This is PMOS and this is NMOS. Okay. The source terminal of the P channel is connected to the source voltage VDD. See, PMOS is connected to VDD and the source terminal N channel is connected to the ground. Here it is connected to the ground. Okay. Then the gate of both the, actually MOSFET having 3 terminals, gate, drain and source. Okay. So, for PMOS this source is connected to VDD and here the source is connected to the ground. Okay. That only they are telling. The gate of both devices are connected together. These are the gate terminal, source, gate and drain, and here also this is drain, gate and source. Okay. So, both the gates, gate of PMOS and gate of NMOS are connected together, and there we are giving the output, sorry, input V in. Okay. So, common input given to both devices, the drain terminal are connected together as a common output. See, the drain of Q1 and drain of Q2 means drain of PMOS and drain of NMOS are connected together and we are getting output. Is it clear? The diagram is clear. See, there are 3 terminals of a NMOS or PMOS. So, this is source, gate and drain. Okay, this is actually NMOS, and similarly for PMOS it will look like this. Here when we are having one bubble, it resembles the PMOS. So, here also the source, gate and drain, this is PMOS. Okay. So, here the source terminal of PMOS is connected to VDD, here the source terminal of NMOS is connected to the ground. Both the gates of NMOS and PMOS are connected together and we are giving a combined input, and both the drain terminal of NMOS and PMOS are connected together and we are taking the output V naught. Okay. So, this is the complete description of the diagram. So, now for a high input at V in, when we are giving 1 to this, we are going to 1 to this, what is happening? When 1 we are giving, then this will be not working and this is working. So, this will be acting as a closed switch. So, V naught will be 0, V naught will be 0 as it will be ground, right. And when we are giving 0, then in that case it will be working and this will be not working. So, this is current V0 will be connected to the VDD. So, in that case the output will be 1. So, it is nothing but the inverter circuit. Okay. So, you can see for a high input at V in, the P channel MOSFET Q1 gets turned off, already I have told, but the N channel device Q2 will be turned on. Okay. This will drive the output V naught to be the logic 0. Got it? If low input is given to the input terminal V in, it will turn on Q1 and turn off Q2, making the output to be high. Got it? So, it is the CMOS inverter circuit. Clear? Next, CMOS NAND gate. Already you have checked what is NAND gate. NAND gate circuit we are already having, this is 0 0. If all the any one of the input is low, then output is high, and if both the inputs are high, then output is 0. So, that thing we are going to implement using CMOS logic. So, here you can take, these are the 2 PMOS, these are PMOS. This bubble you can see, that bubble is the significance is of a PMOS and these are the NMOS. Okay. So, NAND gate is a 2 P channel MOSFET Q1 and Q2. So, Q1 and Q2 are PMOS and Q3 and Q4 are NMOS. A, B are 2 inputs, A and B are the 2 inputs. The input A is given to the gate terminal of Q1 and Q3. See, A is given to Q1 and Q3 and B is given to Q2 and Q4, B is given to Q4, and V naught is taken from the output is obtained from the V naught. Okay. Got it? So, let us discuss. So, these are the 3 cases. Okay. So, when both are 0, A 0, B also 0. So, A was connected to Q3 Q1 and Q3, A is connected to Q1 and Q3 and B is connected to Q2 and Q4. Is it clear? So, in both are this is 0. So, B 0 means Q3 and Q4 both are cut off, and this is PMOS means these are on, this is PMOS. So, Q1 Q3 on. Okay. So, the voltage will be connected to the this VDD. So, V naught will be high. Got it? In second case, Q1 A1 B0 means this is 1, this is 0 means Q1 on and Q3 and this is 0. So, this is also cut off and this is on. Q4 is Q1 and Q4 on, right. Q4, why Q4 on? Because Q1 this connected is to this is the one is going to Q4. So, Q1 and Q4 is on and Q2 and Q3 are off. So, V naught is in this case again will be connected to this to VDD. So, V1 will be V naught will be 1. Third case, when both are 1, when both are 1, in that case these two are cut off, because PMOS, if in PMOS we are giving one high voltage, then both are in non conducting mode. So, it will cut off, Q3 and Q4 will be connecting, and this is the short circuit path. So, V naught will be connected to the ground. So, V naught will be 0. Okay. So, this is I am telling, when both the inputs are given low, it turn on Q1 and Q2 and turn off the MOSFET Q3 and Q4. The output terminal is connected to the supply voltage VDD and the output will be high. This is shown on diagram A, already you have discussed. For diagram B, when either of the input is high, let the because A is high and B is low, in this case MOSFET Q1 and Q4 gets turned on, whereas Q2 Q3 are turned off, and this is B, and this will make the supply voltage to connected to the load again. So, the output will be high. And third case, when both are input are 1, when both A and B are 1, in that case Q1 and Q3 will be cut off and Q2 Q4 will be Q3 and Q4 will be working. So, it will be acting as a closed switch, then the V naught will be directly connected to the ground. So, the output will be low. Okay. So, this is the explanation. Now, this is CMOS NOR gate. In CMOS NOR gate has 2 NMOS and 2 PMOS. So, the Q1 and Q2 are PMOS and Q3 and Q4 are NMOS. So, their input and output connected together A and B. So, let us discuss the cases. Okay. So, first case, A is connected to, you can check it here, A is connected to Q1 and Q3, A is connected to Q1 and Q3, okay, and B is connected to Q2 and Q4. Okay. A is connected to Q1 and Q3, A is connected to Q1 and Q3, and B is connected to Q2 and Q4. Okay. So, when we are giving both as 0, this 2 will be PMOS will be on, but this NMOS are off. Okay. So, the V naught will be directly connected to the VDD, it will be acting as a closed switch. So, V naught will be high. Okay. When A is 0 and B is on, so this PMOS will be on, right, and if it is 0, then this Q3 will be off, but B1 is, this Q3 will be off, but this will be on, this NMOS. Okay. So, in this case Q1 and Q4 on and Q2 or Q3 off. So, V naught will be connected to the ground. So, V naught will be 0. Then third case, when both are 1, A and B both are 1. So, this PMOSs will be cut off and both are NMOSs will be working. So, V naught can check any of the path and it will be connected to the ground. So, it will be giving as 0 output. Okay. So, you can check for low inputs at A and B, PMOS devices Q1 and Q2 will conduct, making the output to be a logic high. When any of the input is low, it will produce a low output as shown in figure B. This is for figure A, logic high. This is for figure A. This is figure A. This is for figure B. When if both the inputs A and B are given high, it will turn on the PMOS devices Q3 and Q4, making the output voltage to be the logic low as shown in figure C. Got it? Clear? So, these are the references, and in this lecture video we have discussed very important topic, CMOS logic family. In there are 3 type of CMOS logic family, NMOS, PMOS and CMOS. Okay. In terms of speed, NMOS and CMOS are better. Okay. So, that is why we are most while designing integrated circuit we go for NMOS and NMOS and CMOS. We have discussed our NMOS inverter circuit, NMOS NAND gate and NMOS NOR gate. PMOS is just similar to NMOS logic, just we have there is the negative voltage, low voltage is enough to turn on the PMOS logic. This is the main important feature of PMOS. And then we have discussed about complementary MOS, CMOS, we are having high speed, less power dissipation, higher fan out, lower noise margin we are having. Then we are discuss about NMOS, CMOS inverter, then CMOS NAND gate and CMOS NOR gate. So, these are the references.